Abstract rewriting system is the formalism that captures the quintessential notion and properties of rewriting systems. In its simplest form, an RRS is a simple set of objects together with some binary relations on this object. And this binary relation traditionally denoted with this arrow. This definition can be further refined if the index or label the subsets of a binary relation. Despite its simplicity, an RS is sufficient to describe important properties of rewriting systems, like normal forms, termination, and various notions of confluence. An RS is actually two things. The first thing is a set A, whose elements are usually called objects, and the second thing is a binary relation on A, traditionally denoted by arrow and called the reduction relation, rewrite relation, or just reduction. In some contexts, it may be beneficial to distinguish between some subsets of rules, i.e. some subsets of the reduction relations, i.e. the entire reduction relation may consist of associativity and commutativity rules. Consequently, some authors define the reduction relation as the indexed union of some relation. For instance, if they have this arrow 1 and arrow 2 relation, they can take the union of these two relations and build a new relation, just arrow. The notation used is A, arrow 1, arrow 2. As a mathematical object, an RS is exactly the same as unlabeled state transition system, and if the relation is considered as an index union, then an RS is the same as a labeled state transition system, with the indices being the labels. The focus of the study and the terminology are different, however. In a state transition system, one is interested in interpreting the labels as actions, whereas in a RS, the focus is on how objects may be transferred or written into other objects. Example, suppose the set of objects is T and it consists of A, B, and C as elements, and the binary relation is given by the rules. We can transform A to B, B to A, and A to C, and B to C. Observe that this rule can be applied to both A and B to get C. So we can start from A and start from B, and we can finish with C. Furthermore, nothing can be applied to C to transform it any further. Such a property is clearly an important one. Okay, let's provide some basic notions. First, they define some basic notions and notations. If they have this arrow with the plus, this means that they have the transitive closure of just arrow. And if they have this arrow with the star, this means that we have reflexive transitive closure of arrow, i.e. the transitive closure of arrow union with equality, with the actually identity relation. Equivalently, we can say that arrow star is the smallest preorder containing arrow. So let's remember that the preorder doesn't have the symmetry. So this means that we can move only in one direction. And also we have the reflexivity. Also, we have somehow this equivalent arrow, and is the symmetric closure of just arrow relation. And it is, we can define it as a union of the arrow relation with the converse of this arrow relation. Also, we can define this equivalence star as a reflexive transitive symmetric closure of this arrow. So this is equivalently is a smallest equivalence relation containing arrow. So, or we can just take this thing, arrow with a star, and add symmetry here, and this will give to us this relation. A very important notion is the notion of the normal forms. An object is x is in A is called reducible if there exists some other y in A and x are reduced to this y. Otherwise, it's called irreducible or a normal form. An object y is called a normal form of x if x are related with the arrow star to y, and y is irreducible. Okay, if x has a unique normal form, then this is usually denoted with the x down arrow. In an example 1 above, C is the normal form, and C is equal to A down arrow and B down arrow. If every object has at least one normal form, the RS is called normalizing. Okay, let's remember this example. So we have this example where we have three elements A, B, and C and such a relation. And you can see that here we can, if we start with A and B, we always end with C. Okay. So this means, actually all this means that in this rewriting system we can have some classes or subsets of objects which can be reduced to one normal form, and this one normal form can represent all the class of these objects. Related by weaker notion that then the existence of a normal forms is that of two objects being joinable. X and Y are said to be joinable if there exists some Z with the property that we can reduce this X to Z, and also we can reduce this Y to Z. In this situation, they say that X and Y is joinable. From this definition, it's apparent one may define the joinability relation as such an operation on these two arrows, where this circle is the composition of relations.